Hello, good morning. How are you doing today?
Good, and you, Professor?
I'm doing well, thank you. All right. 1 second. Okay, all right. So let's take a look at the problem we left off. To calculate the minimum spring constant that's required to keep the block from sliding if it extends 0.12 meters from its unstretched length. Okay, so let's take a look at that. So we have already drawn the free body diagram. And we said in order for the friction to be minimum, you need the static friction to be pointing upward. Okay, so we have done that. Now let's put everything together and figure out what is the spring constant that you need in order for the block to prevent it from slipping. Let's draw the free body diagram one more time, and then we could bring our equations down here. So let me just create another working space. So let's draw it one more time over here. Okay, so to put all the forces on this block, you have gravity, you have normal force, okay, and you have spring force. And the spring constant, we don't know. And we said we want the static friction to be upward to help out with the spring force. So the spring force doesn't have to be as big. Okay, so to set up Newton's second law in the X and Y direction, all the forces has to be balanced. So let's say this is our X and this is our Y. Okay. So gravity, let's break it down into the two components. Have the component pointing down the ramp. So the X direction, and you have a component pointing into the ramp. That's the Y direction. So I'm breaking it down into the two components. This is angle theta, this is theta. Before we set everything up, the relationship between the component and gravity, this is sine theta, mg sine theta, and the Y component is cosine theta. Okay, and now we're gonna put everything together for the X direction. We're gonna put everything together for the Y direction. So any questions so far, what we have done? Does that all look clear? Okay, so let's apply Newton's second law in the X and Y direction. First, let's do the Y direction. There are two forces in the Y direction, and normal force pointing up. Okay, so I'm gonna write plus normal force because this is in the upward direction that's I defined to be positive. And you have the component of gravity in the Y direction, and they have to add up to be 0. So that quickly you have calculated the normal force as mg cosine theta. That is something you probably are already very familiar with at this point, right? For a normal force on the ramp. So now let's set up Newton's second law in the X direction. There are 3 forces in the X direction, 2 of them pointing up the ramp, and that's the spring force and static friction. 1 of the force pointing down the ramp, so that's why I write negative g of x is equal to 0. So you can see that the spring force is equal to f of gx minus static friction. And f of gx is really mg sine theta minus static friction. Okay, so this is what we get. So here, remember our goal. Our goal is to figure out the spring constant. Spring constant. And the spring force is related to the spring constant. Spring force is spring constant times the how much the spring is being stretched, right? Because this is a Hooke's law, you have a linear relationship. So F spring is equal to K times delta X. Delta X is already given to us. We want it to extend for 0.12 meters. Okay, all right. So, and then let's say we want this to be minimum. We want a minimum spring constant, which means we want to find a minimum value for the spring force. So if the spring force is a minimum, what does that mean to our static friction? This does not change. M doesn't change, angle doesn't change. So there's nothing you can do there. So to make this minimum, we need to make this maximum, right? Because if this is a maximum, give us the spring force as a minimum, okay? Because spring force is this constant minus another quantity. So if this quantity is at a max value, I know this spring force is at a minimum value. Well, just so that we know how to calculate static friction for the maximum value, we know that the maximum amount of static friction the surface can provide is equal to, anybody remember? What is the maximum static friction? There is a equation for that. And what is that? Is equal to?
The frictional coefficient for static friction times the normal force.
Yes, very good. Mu sub S times normal force. Very good. Then this is really just the feature of your surface, whatever surface you're dealing with. So there you go. We have found our minimum spring force, and we know all of these quantities. You notice that I'm not trying to plug in numbers at this point. I encourage you to do the same. We will try to get an algebraic equation first, and then you plug in the numbers at the end. The reason for doing that is avoiding possible mistakes. You have less chance to make mistakes. And also sometimes it's easier because some of the variables can cancel throughout the process. You end up not needing the value at all. Okay, so we found our spring force. And at this point, you can plug in values. You can further group mg outside of the parentheses. You have sine theta minus mu s cosine theta. So this is the minimum spring force you will need. You can plug in values. M is given 8.7 kilos. G is given. G you already know. Sine theta you already know. 38 degrees, and plug it in. Mu sub s, it's given by the problem. What do we have for mu sub s? 0.45 times cosine 38 degrees. And you plug in everything, we calculate our spring forces to be 27.6 newtons. Okay, so that is still not the question. The question asks, what is your spring constant at the minimum, right? So we can simply do one more extra step to find our spring constant. We know that the minimum force is 27 newtons, and at this force it's extended for 12 centimeters. So you can plug in 1.12 meters. The minimum spring constant is going to be 230 Newton per meter. So this will be the final result. Describing, okay, what kind of a spring you will need. What is minimum strength of the spring that you will need in order for the block not to slide down. Okay, so that's one problem. That this problem combines the use of a spring force and the static friction on the ramp. So it gets covers a lot of different bases. Any questions about how I solved this problem? Any questions on the process?
Could you briefly go over about the X component? I was a little bit lost on that section.
This component right here?
Yeah.
Yes. Okay, so there are three forces in the x direction. One is the spring force pointing up. One is static friction pointing up. One is gravity, the component of gravity pointing down along the ramp. So since I have set my positive x to be along the ramp up, so these two forces are adding together this positive of the magnitude of these forces. And f of gx is against that direction, so it's minus that force. All of these forces has add up to be 0 because the block is at rest. There's no acceleration, right? Therefore, I got this equation. The rest is just simply by moving around these forces to the other side because I'm solving the spring force. Does that make sense? Did I answer your question?
Yeah. Okay. Thank you.
Thank you for asking. All right, so let's move on. In terms of static friction, there are very interesting things about static friction. So I wanted to talk about two different things before we move on to other topics. So for example, if you have a car, we rely on static friction a lot in our daily lives. For example, when we are going around a circle and we have a centripetal acceleration, we know that already. Even though that we're not changing the speed of our car, we are still changing the velocity of the car. So we do need a centripetal acceleration pointing toward the center. Now, which means there has to be a force, the total force acting on the car has to be pointing toward the center of the track, okay? So so where does this force coming from? So if we were to draw the free body diagram of the car, well, I know that two of them is obvious. We know we have gravity of the car, we know we have normal force of the car, and these two balanced out. And that's no doubt because the car is not going up and down, right? There's no acceleration in the vertical directions. But what about any force in the horizontal direction? That one may not to be too straightforward. Is it actually we have a friction providing the centripetal force that we need that is pointing toward the center. So if your car is at this location, your friction is again toward the center. So this F providing the centripetal acceleration that we need to change the direction of the car. So any guesses on how we manage to have this static friction? Where does this static friction come from? Isn't that the static friction is okay? If you're just sitting here, there shouldn't be any static friction. But if someone try to push you a little, push your chair or your table, then your static friction will be in the opposite direction in the tendency to move. So isn't that our car is just sitting there? Where do we get this static friction? Where does it come from?
The wheels.
Coming from the wheels. Very good. The tires are actually, while you're accelerating with the gas, it's pushing down on the ground. So there is a tendency of which way the car is pushing on the ground, and the ground is providing this static friction to give you the force that you need. So it's from the wheels. Very good. Also very similar to this is like how we walk, right? We are pushing on the ground and the ground pushing back at us, and that will be a separate issue from Newton's third law. But that static friction is coming from the ground, and that is how we gain an acceleration and start walking. If you're originally at rest, then we need to have an acceleration to start walking, and that is where that acceleration is coming from the friction, static friction provided by the ground. So there's a lot of interesting things about static friction. So if you were curious about how fast you can go without skidding off the road, you can simply do a centripetal acceleration. In this case, your static friction is providing F net equals ma, right? And the friction is providing the centripetal acceleration, and acceleration is v squared over r. Okay, So what is the maximum amount of V you can have? We know that the maximum amount of static friction that you can have is going to be mu sub S times normal force, which is mg. So I'm going to replace this by mu mg, and the right-hand side is V max squared over R. So from this, you can see I have calculated the maximum speed you can have is mu sub SGR, because that is the biggest, there is certain static friction the surface and your car can provide, given that velocity, given that radius. If you are faster than that, then this static friction is not enough to hold you in that track. Therefore, you will slide off to the outer rim. Okay, so that's how you calculate the maximum amount of force that the car could go around without sliding off the rim. One more other interesting features about static friction has to do with this particular question that you've done. Here you have a big truck with an acceleration to the left. Here there's a box sitting still relative to the truck is sitting at rest. So which of the diagram is the correct diagram showing the static friction force that is acting on the box? Okay. So which one do you think is correct? Is it C that?
Is it B? Or is it, yeah, I don't know.
So one possible reason for C might be, well, the box is at rest. So therefore, no friction. Someone might argue, well, the box is not, is at rest, so there's no tendency for sliding away. So that might be, now if you were trying to think about in which way the truck is trying to move, okay, you might think, okay, the truck is moving left, maybe the box will have a friction pointing to the right, in which case that might lead to option B. So I would say that this is, there, if you think of those, it's gonna be hard to figure out which one it is. So we can change our point of view to think about, okay, what is the status of motion of the box and what kind of acceleration the box has? And that will tell us which way the static friction has to be pointing at, okay? So, so what can we say about the box acceleration? Is it 0 or is it non-zero? Is it, if it's non-zero, is it pointing to the right or is it pointing to the left, just like the truck?
Its acceleration has to be to the left, pointing with the truck, because like it's inside the truck. So it's kind of like when you ride a car, you don't just stay behind.
Very good one, and very good, Jacob. It has to be to the left, just like the truck, because otherwise it will be sliding backwards because the truck is going forward. So even though it is not explicitly telling you, we know implied the acceleration of the box is also to the left. So there must be a force, the net force acting on the box must be to the left, right? So let's analyze the forces. Obviously, we have the weight of the box, and we do always have the normal force. And that's in the vertical direction. We need a force that is in the horizontal direction, or if you think there are multiple forces, then the overall of the forces has to add up to be in the same direction of its acceleration. And the only possible force that can provide such an acceleration would be the static frictional force, right? And it's pointing to the left. So we know that, well, A has to be correct. Okay, that is the only possible choice for the box to be moving together with the truck. Okay, now if you were to, yes, go ahead.
I just had a question. Is there a correlation between the direction of acceleration and static friction in which they will face the same direction always?
Not necessarily, depend on what other forces is at play here. So if there are other forces also in the x direction, then we will need to think about all the forces adding up to be pointing in the direction of the acceleration. So there's no a direct correlation between static friction and acceleration. This is just one example to show that not a very familiar case where you have done static friction, right? It's a little bit different. If you were to try to think about how does the static friction come into effect is when your trucks start going this way, then the box have a tendency relative to the truck sliding backwards, okay? But if you have a surface that's rough enough, and if the box is heavy enough, then to prevent the slipping backwards, your static friction will be opposite to that direction, so pointing forward, and that carries the whole object and carries along with it, right? So that is pretty much, you know, we have stuff inside a car, we're driving with it all the time. So that's how the object gain its acceleration is through the static friction between surface. Now, of course, you have seat belt, and that helps as well. But I'm just talking about if you just have a box or a cargo, something like that. Any questions?
So then essentially the static friction would be in the direction of acceleration, because otherwise if it was on the opposite direction, it would be sliding backwards, correct?
Yes, in this case, yes. Without
Because-
any other forces in the x direction, yes.
And it's so because of the forces are balanced, right? Because of the normal, it's pointing towards the acceleration because in this case, the normal force and the gravitational force is balanced, correct?
Yes, the y direction has no acceleration, and the only acceleration is in the x direction, and that is provided by the friction. Yes, you're correct.
Okay, so if they weren't balanced, and then that would change the static friction, correct?
Oh, you mean like if the vertical direction is not balanced?
Yeah, so like if so for instance, if there was force in the, because in this case there's no motion going on in the y direction. So if there was in the y direction, then it would change the static friction, correct?
Yeah, like if you wanted to lift it up, obviously you would change it in the y direction.
Right. Okay. Thank you.
Okay, thank you. Thank you for the question. Very good. Okay, so let's move on to talk about a different type of problems that has to do. This is also a classic set of problems that has a pulley, has tension in it. And you have done a lab. I think you probably all have done the lab, depending on which lab session you're in. Then in our lab, we have a hay mass, we have a little cart, and then all the whole setup is moving along. So let's look at this bridge question you have already done, where we have two scenarios. Case one, there's no friction, and M1 is dragging on M2. The whole setup is just simply moving in this direction. Case two, there is friction. The whole setup is moving in the same direction, in which case the tension is biggest. Okay, so I just want to use this bridge question opportunity to solve such a problem. We solve for the tension in case one, and we solve for the tension in case two, and then obviously we could compare. But the important thing is let's just figure out how to deal with this type of questions. So let's look at the scenario where there's no friction, just the two objects, okay? We can break it down into a few different questions. So for example, we know exactly how to solve for tension when the whole setup is hold motionless. If you have a little stop right here, nothing is moving. What about the tension in the strain right now? So I'm gonna let you guys go ahead and let me know what you think. That should be a fairly straightforward and quick vote. Okay, 10 more seconds. If you haven't put in your thought, please go ahead and vote. All right, any last minute vote? All right, if not, let me close it and let's take a look at our thoughts. All right, so you can see that it's telling us the card is hold motionless, right? If we focus our attention on the card, we might be reaching the impasse. We don't really know where to go. The card, okay, we have attention dragging on the card and there's a block pushing the card back. I don't really know what the forces are. So, but instead, we should focus our attention on which object to figure out tension. To find out what's the tension in the string, we need to focus our attention on the hanging mass, right? As you guys figure out that, oh, M1G is exactly the weight of the hanging mass. So the free body diagram on a M1 is M1G, weight pointing down and the tension pointing up. And the card is motionless, which means this object is also motionless, no acceleration. And the tension has to balance out the weight of M1. A is correct, very good. So it's A, okay? So this is a direct application of Newton's second law when everything is balanced. All right, now let's release the card. So all the object is moving. You can probably already guess, or even though we haven't solved it, you know, compare with the original value M1G, should it be bigger now or smaller one? Smaller now. If it's exactly the same as before, it's not going to have an acceleration, right? We have already established that. That is when the card is at rest. And now if everything is moving, what about the tension in the string? So let's look at M1 again. M1 has gravity pointing down, that's M1G, and it has tension pointing up. Okay, so before we have tension exactly balance out gravity, exact same length of arrow pointing up. But now we have a downward acceleration. Do you think the tension now is bigger, in which case I will draw it like this? Or do you think my tension is smaller, in which case I would draw it like this? What do you think?
The tension is smaller.
Tension is smaller, and why is that?
Because the object is, the mass one is moving downwards now. So the mass times gravity is greater than the tension.
Yeah, very good. From the graph, we can intuitively see you want the downward arrow to be longer, so the net force adding up to be also downward, just like the acceleration. Excellent. So it's C. It's smaller. Now let's calculate it. So you do have this question on the handout. If we were in class, I will print this out for you, but it's on the canvas. We don't really need the handout to do this calculation. So let's just try to do the calculation together. Can we calculate the tension? All right, so we have two different objects. Pulley. So no friction here. Makes things a little bit easier to calculate. And you have M1 here. If you have already done the lab, you probably know what we are going to do, right? We will set up Newton's second law on M1. We will set up Newton's second law on M2. And we solve for the acceleration. We can also solve for the tension. So that is totally fine. Okay. I can show you that, but I also want to show you more of a sort of a trick that may speed up the process just a little bit. So in the scenario like this, we established that they both have the same acceleration, right? Because they're moving together. They have the same velocity, they have the same acceleration. So if I view M1 and 2 and along with the string as an entire object, they are all connected together, right? So I'm going to view them as one piece. So if I do that, and they're moving in this direction. So how fast they speed up or slow down? What is the acceleration? Will depend on the different forces that's acting along in that direction. So you can see that if I view them as an entire piece, what is the force that is responsible for speeding them up? Which is what force?
The force of mass 1 times gravity.
Yes, it's the weight of mass 1 that is responsible for speeding up this system that we call this entire thing our system. Okay, so that is gravity, M1, G. I'm just going to call weight 1, which is M1, G. Is there any other force that is responsible for speeding them up? If you think no, then just say no. Not weight M2G, right? Weight M2G doesn't do anything to speed them up. That because it's in this direction, right? We want it to move along in this direction, okay? So not the weight of M2G. M2G's weight is balanced by the normal force, so it doesn't really help us, okay? All right, so I'm gonna get rid of this.
So would it just be M1G then? That changes the acceleration?
It would just be M1G. Very good. That's it. Now, if you do have friction, if there is friction, then you will have a friction to slow them down, to be responsible to slow them down. But we are working with a situation where you don't have friction. So you only have really just one force acting in this direction where they're accelerating, okay? And you can see what's so good about this method is a shortcut that you don't have to think about tension in this case, because tension is within the system, is part of the system, and you cannot really give a force to you. It's like you cannot accelerate yourself. Use your left hand to push your right hand, but your whole body is still here. You're not going forward, right? So tension is kind of like that. It's within the system. It doesn't really do anything. So we don't even have to think about tension. So the only force that is responsible to speed up the system, which the system now consists of M1 and M2 accelerated together, is just the weight of M1. So you can see that we can quickly calculate the acceleration of the entire system by using this trick. So A acceleration is M1G divided by M1 plus M2. You will get the same result if you had set up the Newton's second law twice on M1 and on M2. Okay, so if you were to do that, this was from your lab. I can do it relatively quick here. If you were to do that, you would say, okay, on M1, you have M1G pointing down, you have tension pointing up. Then I would write M1G minus tension is M1 times the acceleration of 1, which is the same acceleration of 2. If I do this M2, I would say, well, okay, only force that's responsible for speeding it up is the tension. Then I do tension is equal to M2A. And then you can plug in tension here. You get M1G minus M2A equals M1A. You get the same result. M1G is equal to M1 plus M2A, and you can solve for the acceleration. Okay, so you can see that it's the same result as previously. It's a little bit longer. Okay, all right. But if you feel like this is clear, I think maybe you will find this much more clear, focusing on one object at a time, then by all means do that. That's totally fine. Now to find the tension, you realize, well, okay, this shortcut only get us to get the acceleration. We still need to focus on either one of the objects if you want tension. So it's probably easier to focus on M2 because the only force acting on M2, well, if you want to focus on M2, then you isolate this object by itself, then the only force that's speeding it up is tension. So tension is M2 times the acceleration, which is M1G over N1 plus M2. So this is our tension. The tension here for this case. Can you solve it? Yes, the tension is M1, M2, G divided by M1 plus M2. So this is a tension if you were to release the system, let the cart go, and there's no friction on the table. There's no friction on the surface. So this is the tension. We have solved it. We just need to do that for where there is friction, and then you can compare. So any questions so far about how I solved for the tension and the strain for the no friction scenario? Any questions?
So then the other example, like below where you have the line cross, that's with friction.
I'm sorry, say it. Yeah, the case 2 is friction. Then we will add friction to modify our answers.
No, but I mean like on your actual screen, you see like where you drew the horizontal line.
Oh, this line? This line?
No, the you see where you have A equals M1 G over M1 plus M2,
Yes.
and then like the big horizontal line like dividing the screen.
Oh. This is, okay, so I should, yes, this is 2 different methods for the same case. So this is case 1. So this method is the trick, is a shortcut. So this is viewing M1 and M2 and strain as an entire system. Okay, so this is another method. This is the method, 2 methods, method 1 or 2, where you view M1 and M2 separately. Does it make sense? So if you view them together, that's a shortcut that gets you the acceleration much faster. You don't have to think about tension when you set up your force equation to do the acceleration. But you do have to go back to the individual system to find tension later.
Okay.
For the second method, you view M1 and M2 separately and you draw free body diagrams separately. You find acceleration and you can also find tension. There is not, maybe not a drastic difference between these 2 methods. But when you have friction, maybe these methods will be a little bit more different.
Wait, I'm a little confused. How come tension for M2 is pointed to the right instead of pointing to the other, instead of pointing to the left?
Tension on M2, well, isn't that rope dragging M2 though?
Oh, okay. Actually,
Right,
oh,
so
okay.
to
It's
the
moving.
right. Yeah, it's speeding up to the right, right?
Okay, yeah, I see.
Okay, any other questions on these 2 methods? Okay, now let's look at where you have friction, okay? Then the only difference you need is to add a friction here. So all the method you have done also works. You just need to add friction here. So let me show you, I'm not gonna write everything now, but I'm gonna show you my slides. How do you view M1 and M2 separately to solve for the tension and the acceleration? So if you look at them separately, you draw the free body diagram on 1 and 2 separately. M1 doesn't change, it's still tension and weight. And 2, now you have added the friction, right? That's the only difference from our previous situation. And you do free body diagram on both of them. So everything stayed the same. So for M1 is still weight minus tension is M1A. For M2 is tension minus friction is equal to M2A, right? So you're applying Newton's second law on both of them. And then friction, kinetic friction, let's remind ourselves, is mu sub k times normal force. So mu sub k is the kinetic coefficient describing the surface features, how rough your surface is, and normal force is the weight of m2. So that's why I have mu k m2g. Okay, so you have two equations. You can add them together, or you can say solve for tension and plug in into the other one. There are some algebra to be done. You can do that later and verify this for yourself. But once you have these two equations, you can solve for the acceleration. You can also solve for tension, because you can plug in the acceleration to either one of them and you get your tension. So if I plug in acceleration in here, I got tension is equal to m1g minus m1a. Okay, so which is m1 g minus m1 times a. What is a? A is this entire thing, so it's a little long. Okay, I could you can combine this just a little bit more, m1 and 2. So the first term, this term, if you multiply m1 divided by m1 plus m2, you need to multiply it by m1 and 2, so it becomes m1 g m1 plus m2, and then you have the second term that's here, m1 squared g plus mu k m1 m2 g. Don't worry too much about the algebra I'm doing. You can always verify it later. Okay, and clean it up a little bit more. M1 squared g, m1 squared g, the first term cancel out. So you get m1, m2g plus mu sub k, m1, m2g over m1 plus m2. All right, so that is my tension for the case 2. So you can see that if I were to do the shortcut, I can get my acceleration a little bit faster. So I'll show you how. So if I were to view M1, M2 together as entire piece, so what would happen is, so this is my M2. This is the M1. Now let me view this as entire piece just to remind myself. I have, which force is responsible for speeding it up is the M1G, is the weight. Sorry, weight 1. Which force is responsible for slowing down? Different than before, you added a friction, right? You didn't have that, but now you have it. So that's it. That's the two forces acting on this entire system that has anything to do with acceleration. The normal force here, it does not come into the direction of the acceleration. Okay, that's why you could choose not to draw it just to not to confuse yourself. Okay, so you do Newton's second law for the entire system, which is M1 and M2 together. You will have M1G minus friction is equal to M1 plus M2A. Now friction is mu times M2G. That's the normal force. So that's just one extra step you need to go. And you can see I get the same result as I got previously, which is M1G. You have a weight, now you have friction to slow it down, and all of that force is speeding up the entire process, object M1 and M2. So it's the same result you got here. Okay, just a little bit faster. Maybe it wouldn't matter too much to you. But I think it's a bit faster.
Should we always try both methods to check our acceleration if it's like it matches?
You can if you want, but I would say if you have the time, you could, avoiding making mistakes. But if you're rushing through time, like on the quiz or something, then just stick with one method, whichever you feel more comfortable with. Okay, all right, so that is the shortcut. Again, this is the shortcut. To find the tension, you still have to go to individual objects to find the tension. And that's just like the same we did before. So the next step is exactly the same as we did previously. All right, so do you have our tension here? So now you have everything, you could compare your tension. This tension is M1, M2G divided by the total mass. This tension is M1, M2G add in an extra something divided by the total mass. So it is clear from your result that tension in case 2 is bigger than tension in case 1. Okay. All right, so lastly, there are set of problems where we deal with multiple objects. For example, here we have a net force. Here it's already tell you this is a net force. So you don't have to think about, okay, friction, whatever, it's already considered together is a net force, F total. It's acting on mass 1, give you an acceleration A1. The same net force acts on mass 2, give you acceleration A2. A2 is twice of the acceleration of A1. Okay, so that probably told you something about the masses. So if A2 is 2 times of A1, what can you say about mass 2? Is mass 2, how is mass 2 related to mass 1?
Is it half of it?
It's half of it, right? Because the smaller the mass, the bigger the acceleration. So if the acceleration doubles, which means you have half of the mass. Very good. Now, if you put these two together and you push it with the same force, you get an A3. And what is that, A3? Okay, so we don't have time to do breakout room, so I'm going to solve this for you guys. So let's just apply Newton's second law on the third situation where F, the total force is acting on M1 and M2 together, give it a third different kind of acceleration. The force is still the same force, M1 plus M2 times A3. We had just figured out the mass relationship between them, right? So mass 2 is half of mass 1. So mass 2 is 1/2 of mass 1. Okay, so 1/2 M1 to replace M2. And that becomes 3/2 of M1 times A3 is equal to F. So how is A3 related to A1? Well, I know that when this force is applied on M1, it gives me an acceleration A1. That is what described in the first picture. So if I combine these two equations and compare them, you can see that, okay, this is more of the mass, so A3 is going to be smaller, right? A3 is going to be 2/3 of A1. Or you simply just do substitution of F over here, M1, A1 is equal to F is equal to 3/2 M1, A3. So you can figure out A3 is 2/3 of A1. Or you simply divide these two equations and do a proportion where the force cancels out. Sorry, it's not updated. Just let me try this one more time, but we're pretty much done. Whichever method you use to do your math, eventually you will get the A3 is 2/3 of A1. Okay, so that's our result. So it's 2/3 of A1. And I looked at it, I know, okay, that is the correct answer. So when you have multiple objects, that's one example of how to deal with multiple objects. We will do a little bit more of that later when we do Newton's third law. All right, so that's all for today. Sorry, I went over for a couple minutes. I'll see you guys on Friday. Bye, everyone. Have a nice day.
Bye, Professor. Have a good day.
Thank you. Bye-bye.